Determine the internal normal force, shear force, and moment acting at point C and at point D. Point D is located just to the right of the roller at support B. To begin, make our life easy, we're just going to use right hand side of this beam. That means we'll only need external action force for B and none for A. To begin solving, we first convert our uniform distributed load into point loads. So our side loads going to be 2 times 4, which is 800 pounds. And then our in-between load is going to be 300 pounds times 8, which is 2400 pounds. Now we can find our solution for By, which can be found taking moment about the point A. So we can have counterclockwise 800 pounds times 2 feet, and then clockwise 2400 pounds times 4 feet. Then we have our unknown By, which is counterclockwise, and that's 8 feet away. And finally our clockwise 800 feet or pounds, and then times by 10 feet, all equals to 0. Our By come up to be 200 pounds, 2000 pounds. Now that we have our By, we can start solving for this problem. We'll start with point D, so let's draw its free body diagram. We're going to have point E, and in between point P and E, we're going to have 800 pounds. And then we have our break at point D, where we're going to have our shear, our normal, and our moment. Finding shear is simply going to be negative 800 pound, which means traction of the shear will be upwards. Then our normal is going to be 0 because there isn't any other horizontal force acting on it. And finally, to find our moment at D, just have to take a moment about the point D, and it's a super simple equation for this problem. It's going to be clockwise moment at D, and then clockwise 800 pounds times 2 feet equals to 0. Solve for moment D, we're going to have our solution as 1600 pounds foot, and it's going to be negative. Now we can move to point C. Point C, our initial diagram on the right hand side is going to be similar to point D, where we have 800 pounds between point B and E. And at B we have By of 2000 pounds, which is our external reaction force. And then at point C, where we have the cut, we're going to have our shear, our normal, and our moment. And we're also going to have our distributed load part of it, so it's going to be 300 pounds per foot times 400 or 4 feet, which is going to be 1200 pounds, and it's going to be 2 feet away from C, or you can say from B. All right, now that we have these values, we can solve for our shear, which is going to be by summing the forces in the y direction. We're going to have our shear, our 1200 pounds, positive 2000 pounds, negative 800 pounds, all equals to 0, which comes up to be equals to 0. And then our shear, normal force is also going to be 0. And now to find our moment, we can take moment about the point C. We're going to have clockwise moment C, clockwise 1200 pounds, and it's 2 feet away from C. Then counterclockwise 2,000 pounds, 4 feet away from C. And then finally clockwise 800 pounds, 6 feet away from C, all equals to 0. Solving for moment at C, we get our solution as positive 800 pounds, 8. Determine the internal normal force, shear force, and bending moment at point D. Take uniform distributed load as 150 Newton per meter. Part 2. The beam AB will fail if the maximum internal moment at D reaches 800 newtons meter, or the normal force in the member BC becomes 1500 Newton. Determine the largest load W it can support. Alright, to do the first part, first of all we need to draw our external reaction forces. So we're going to have AY, AX, CY, and CX, and then our distributed load is going to be 150 times 8, which is 1200 Newton. To solve this, we need to take our moment or our diagram pen to pen. So to solve this, we can have free body diagram for AB. It's going to be something like this, where we have AY, AX, point load of 1200 newtons, and our unknown force BC. To begin, we're going to have moment at point A. So it'll be 1200 newtons clockwise, 4 meters away. And then counterclockwise, force BC, or its vertical component of force BC, times the distance from A, which is 8, all equals to 0. Solving for force BC, we get our solution as 1000 newtons. Now we can find our value for AY. As in the forces in y direction, we're going to have 1200 newtons, negative, positive force BC and its vertical component, and then positive AY. Solving for AY, we get a solution as 600 newtons. Now we can cut our member at point D to find our solution. So we're going to have our free body diagram look something like this. So 150 times 4 is 600 as our point load, and it's 2 meters away from E. And then our force BC, which is 1000 Newton. Pardon me, we don't have force BC because we are cutting it at D. So we're going to have our shear, our normal, and our moment. Our shear is going to be 0 Newton, and so is our normal. Pardon me, normal will not be 0 because we have force BC acting on this beam. And earlier we haven't calculated, so we're going to do that right now. So we'll have another force which is going to be simply sum of forces in x direction. So we're going to have AX positive, and then negative force BC, which is 1000, its horizontal component, which is 4 divided by 5, all equals to 0. Solving for AX, we get our solution as 800 newtons. And now our normal is going to be AX, which is 800 positive. Then we have positive. Normal force all equals to 0. Solving it further, we get our normal as negative 800 newtons. And then finally our moment. To find our moment at D, we can take moment about the point D. We're going to have counterclockwise 600 newtons times 2, take away clockwise 600 newtons times 4 is equal to 0. And another thing I forgot is positive moment D, all equals to 0. Solving for moment at D, we get our solution as 1200 newton meter. For the second part, we have to find our distributed load when either moment reaches 800 pounds or the normal force at 1500. And looking at our part 1, we know that internal moment is going to be the defining factor. Therefore, we're going to use our moment to find our ultimate value of distributed load. So for that, we're going to use this equation here. So we're going to have some moment at D. But in this case, we don't know our AY yet, which is 4 meters away. We don't know our point load, which is going to be W times the whole distance, which is in this case 4 meters, times how far is it away from D? 2 meters. And then finally our moment at D, which is 800 in this case, Newton meter, equals to 0. Now to find our Y, well, first of all, I have to simplify this equation. So we're going to have negative 4AY positive 8W equals to negative 800 newtons. We're going to name it our equation 1. Now we're going to go back to our earlier equation where we took moment at point A. But the only difference we're going to have is instead of taking moment about the point A, we can take moment about the point B. So we're going to have our W, which in this case is going to be 800 meters to find our point load. And then it's going to be 4 meters away from B. And it's counterclockwise, so positive. And then we have clockwise AY, and it's 8 meters away. All equals to 0. And this is going to be our second equation where it's going to be 8 4s are 32. W take away 8 AY equals to 0. And now we can solve for this equation simultaneously. So we're going to have negative 4AY positive 8W equals to negative 800. Then we have our 32W positive negative 8AY equals to 0. Now we're going to subtract this whole thing. So this is going to be positive, this is going to be negative. We're going to have negative 800 negative 24W and positive 4 AY. Now we're going to separate into one variable here. So it's going to be AY equals to negative 800 positive 24 W divided by 4. Simplifying it further, we're going to have negative 200 plus 6W equals to AY. Now we can plug the value of AY into one of our equations here. So we're going to do it for equation 2. So we're going to have 32W take away 80Y. But AY in this case is going to be negative 200 plus 6W equals to 0. Simplifying it further, we're going to have negative 32 we're going to have positive 1600 negative 48W equals to 0. Thirty-two take away 48 is 16, so it's going to be negative 16W equals to negative 1600. And solving for W, we get our solution as 100 Newton per meter. Now we can plug the value into one of the equations here to get our solution for AY. So we're going to use or do that by plugging the value into equation 2. So we're going to have 32 times 100 for W take away 8 AY equals to 0. Solving for AY, we get our solution as 400 Newton per meter.